Welcome to this class of sound through slideshow. Today's chapter is stationary waves. We confine our discussion to the stationary waves on stretched strings. We proceed to answer the following questions. How a stationary wave is formed? How it appears? And what is the analyzation of a stationary wave? What are the properties of the stationary waves? What are the modes of vibration of a stretched string? What is the relation between the length of the wire and the wavelength of the wave that travels on this stretched string? What is the relationship that we can use for finding the speed of this transverse wave? And then, what is the frequency with which a stretched string can be vibrated? We try to answer these questions. Now we proceed as follows. First, the formation of a stationary wave. And the waves, the composite waves, which produce stationary waves. How the wave is represented. Then we study the properties of these waves. The mathematical equation that can be used for studying these waves. Then the positions of nodes and antinodes. The speed of the transverse wave will be discussed. And then the modes of vibration of the stretched string will be discussed. Then the relation between the length of the wire and the wavelength of the wave. Finally, the frequency of vibration of a stretched string will be discussed. This is the way in which I am going to proceed. Then the lesson will be summarized and then a test appears before you. Consider two waves traveling in opposite directions. Two waves traveling in opposite directions along the same line. When they get superimposed, then the resultant wave is called a stationary wave. So a stationary wave is formed by the superimposition of two waves traveling opposite directions. Generally, we consider the two waves of same frequency, same amplitude of vibration. Stationary waves can be produced by the superimposition of either two transverse waves or two longitudinal waves. Stationary waves can be produced by the superimposition of transverse waves or longitudinal waves. For example, when we take the stationary waves on a stretched string, they are produced by the superimposition of two transverse waves. On stretched strings, the superimposition of transverse waves takes place, whereas in resonance tubes, it is the superimposition of longitudinal waves that produces stationary waves. So, stationary waves on stretched strings are due to the superimposition of transverse waves, and stationary waves in resonance pipes are due to the superimposition of longitudinal waves. When we observe the stationary waves on a stretched string, we notice loops as shown in the figure. Here, one wave proceeds to the right, the other wave proceeds to the left. So, due to the superposition of these two waves, the stationary waves are formed. AN indicates antinode, N indicates node. Antinode is the point of the particle where the amplitude of vibration is maximum. Antinode is the position where the amplitude of vibration of the particle is maximum. Node is the point where the amplitude of vibration is minimum. If the amplitudes of the two waves are equal, then the vibrational amplitude of the node is 0. If the amplitudes of the individual waves are equal, then the node will be 0 amplitude. Then the region between two nodes is generally called as a loop. The region between two nodes is called as a loop. The distance of this loop, that is, the distance between two successive nodes, is lambda by 2. Similarly, the distance between two successive antinodes will be lambda by 2. The distance between two successive nodes or the distance between two successive antinodes is lambda by 2. Let us proceed to analyze the properties of the stationary waves. We notice that loops are formed when stationary waves are formed. Loops will be observed due to the formation of stationary waves. We know that a loop is the region between two nodes. As we observe the amplitudes of vibrations of different particles, the amplitude is different for different particles. The arrow marks indicate, the length of the arrow mark indicates the amplitude of vibration. So the amplitude of vibration increases for the particles from node to antinode, and it decreases from antinode to node. So at antinode, the amplitude of vibration is maximum. If the two waves, superimposing waves, have equal amplitude, then the amplitude of vibration of node is 0. The stationary waves sometimes can be expressed in terms of pressure waves. Sound waves can be expressed in terms of pressure waves. So the pressure variation takes place, and the variation of pressure is maximum at nodes. In case of sound waves, the pressure variation is maximum at nodes and it will be minimum at antinodes. This is in the case of stationary waves formed by sound. Let us continue the discussion of properties. We have seen that the distance between two successive nodes or between two successive antinodes is lambda by 2. So the distance between a node and its immediate antinode is lambda by 4. The distance between a node and its neighboring antinode is lambda by 4. Though different particles have different amplitudes of vibration, but the period of vibration of all the particles will be the same. The period of vibration of all the particles is the same, so also the frequency. All particles vibrate with the same frequency. But when these particles they cross their mean position, they will have maximum velocity at mean position. That means the velocity at mean position at that point will be different for different particles. So the maximum velocity which is attained by the particles at the equilibrium position will be different for different particles, and it is maximum for particles of antinode. So the velocity at equilibrium position is maximum for particles which are situated at antinodes. Let us proceed with these properties. In stationary waves, the energy is not transported by the wave. The energy will be confined to the medium and it will not be transported because the vibration is not transmitted by the particles. The vibration is not transmitted by the particles, hence no energy will be transmitted through the medium. All the particles will be at the equilibrium position simultaneously, that too twice in a period. In a period, all the particles will be in the equilibrium position twice, that too simultaneously. All of them will come to the equilibrium position simultaneously twice in a period. The particles in the same loop will have the same phase. Consider the dots 1, 2, 3 from left. The first two dots will have the same phase because they are in the same loop. The third dot is in the neighboring loop, so it will have pi phase difference with the two dots. Similarly, if you consider another particle in the first loop, it will have a phase difference of pi with the two dots in the second loop. Like this, the particles in the neighboring loops will have a phase difference of pi. Now let us represent the waves by mathematics. A wave proceeding along the positive direction of x-axis. A wave which travels along the positive direction of x-axis is represented by y is equal to a sin omega t minus kx. Y is equal to a sin omega t minus kx. A wave traveling to the left, that is the negative direction of x-axis, is represented by y is equal to a sin omega t plus kx. A wave traveling along the positive direction of x-axis is represented by y is equal to a sin omega t minus kx, that is first one. The second equation, y is equal to a sin omega t plus kx. This is the equation that represents a wave traveling along the negative direction of x-axis. When these two waves get superimposed, then we will get stationary wave. The equation of the stationary wave will be obtained as y is equal to 2a cos kx sin omega t. The equation of the resultant wave, stationary wave, is given by y is equal to 2a cos kx sin omega t. Here k is known as propagation constant and it is given by 2 pi by lambda. K is propagation constant and its value is 2 pi by lambda. Omega is angular frequency. It is given by 2 pi by t or 2 pi nu. We represent the wave equations like this. We use the notations k for 2 pi by lambda and omega for 2 pi by t or 2 pi nu. When stationary waves are formed on a stretched string, how to locate the positions of nodes and antinodes, how to calculate the positions of nodes and antinodes using mathematical relations. First, at the left end, if a node is formed, then at a distance of lambda by 4, antinode is formed. If we proceed to measure the distances from left end, so the position of the node will be at x is equal to 0. So at x is equal to 0, a node will be formed. And next node will be formed at a distance lambda by 2. So the positions of nodes will be 0, lambda by 2, lambda, 3 lambda by 2, etc. The distance of first antinode will be at a distance lambda by 4, because at the end a node will be formed. So antinode will be formed at a distance lambda by 4. So the first antinode will be formed at a distance lambda by 4. The next antinode will be formed at 3 lambda by 4, because the distance between two successive antinodes is lambda by 2. So the positions of antinodes are lambda by 4, 3 lambda by 4, 5 lambda by 4, etc. So positions of nodes are 0, lambda by 2, lambda, 3 lambda by 2, etc. Antinodes positions will be lambda by 4, 3 lambda by 4, 5 lambda by 4, etc. By using these relations, we can calculate the positions of nodes and antinodes. What is the speed with which the transverse wave travels on the stretched string? The speed depends on the tension in the string and the linear density of the wire. The speed of the transverse wave on a stretched string depends on the tension and the linear density of the wire. Actually, the relation is given by V is equal to square root of T by M, where T represents tension and M represents linear density. If at the end of a string a mass capital M is attached, then mg becomes the tension. And the linear density is given by small m is equal to pi r square d, where r represents the radius of the wire and d represents the density of the material. So linear density small m is pi r square d. So using the values of tension and linear density, we can calculate the speed of transverse wave on a stretched string. Modes of vibration of stretched string. A stretched string can be vibrated in different modes. If it is vibrated as a single loop, it is called fundamental mode of vibration. Fundamental mode of vibration is that mode in which the entire wire vibrates as a single loop. Then the wavelength becomes equal to twice the length of the wire. This is also known as first harmonic. The frequency of vibration in this mode is known as first harmonic. This wire, the same wire, can be vibrated in two loops. Then it is first overtone mode. This is first overtone mode, or the frequency of vibration in this mode is twice that of the fundamental mode, and this is called second harmonic. The frequency of vibration in this mode is known as second harmonic. The same wire can be vibrated in three loops. This is second overtone mode. The frequency is known as third harmonic. If the wire is vibrated in four loops, this is third overtone or fourth harmonic. So the same wire can be set in vibration in different modes. Now let us proceed to find the relation between wavelength and length of the wire. Just now we have seen that a stretched wire can be vibrated in different modes. If the wire is vibrated in P loops and the wavelength of the wave is lambda, then the length of the wire L will be equal to P into lambda by 2, because the loop length is lambda by 2. So L will be equal to P into lambda by 2 if the wire is vibrated in P loops. In the fundamental mode of vibration, if the wavelength is lambda 1, then the length of the wire L will be equal to lambda 1 by 2. If the wire is vibrated in two loops, and in this case the wavelength is say lambda 2, for two loops the length will be 2 into lambda 2 by 2. So the length of the wire L will be equal to 2 into lambda 2 by 2. If the same wire is vibrated in three loops and the wavelength in this case is lambda 3, then 3 into lambda 3 by 2 will be equal to the length of the wire. The length of the wire will be equal to 3 times lambda 3 by 2. If the wire is vibrated in 4 loops, then the length of the wire will be equal to 4 into lambda 4 by 2, where lambda 4 is the wavelength when the wire is vibrated in 4 loops. So in general, the relation between the length of the wire and wavelength is L is equal to P into lambda by 2, or lambda is equal to 2L by P. Lambda is equal to 2L by P. Using this relation, we can find the wavelength of the wave. Frequency of vibration of stretched strings. Let us derive the relation for frequency of vibration. We know the relation for the speed of a wave in terms of wavelength and frequency is given by V is equal to n lambda. V is equal to n lambda gives the relation between speed, frequency and wavelength. So in the case of the first harmonic, that is when the string is vibrated in the fundamental mode, the wavelength lambda 1 is equal to 2L. The wavelength lambda is equal to lambda 1 is equal to 2L. From the above relation, we will get the frequency, first harmonic N1 is equal to V by lambda 1. From the relation V is equal to n lambda, we will get N1 is equal to V by lambda 1. The speed of the wave in a stretched string is given by root T by M. So substituting the values of V and lambda 1, we get the relation 1 by 2L into root T by M. This is the relation for frequency in the fundamental mode of vibration. So in the fundamental mode of vibration, the relation for frequency of vibration is given by N1 is equal to 1 by 2L into square root of T by M. In the next mode, when the string is vibrated in two segments, the wavelength lambda 2 is given by 2L by 2. L is equal to 2 lambda 2 divided by 2, from which we will get lambda 2 is equal to 2L by 2. So substituting this value, we get N2 is equal to 2 by 2L into square root of T by M. When the string is vibrated in 3 loops, then lambda 3, wavelength lambda 3 will be equal to 2L by 3. Hence we will get N3 is equal to 3 by 2L into root T by M. Like this, we will get the frequency in each mode. When the string is vibrated in 4 segments, the frequency N4 is equal to 4 by 2L into square root of T by M. So in general, if the string is vibrated in P loops, the relation for frequency is given by P by 2L into square root of T by M. Like this, we can calculate the frequency of vibration of a stretched string. So the frequency of vibration depends on the mode of vibration. It changes with the mode of vibration. Stationary waves on a stretched string are formed by the superimposition of two transverse waves. Stationary waves on stretched string are due to two transverse waves, superimposition of two transverse waves. Then the stretched string appears in the form of loops. The length of a loop will be equal to lambda by 2. And a stretched string can be vibrated in different modes. It can be vibrated in a single loop, or in 2 loops, or in 3 loops, etc. Then the positions of nodes will be obtained from the following relation. Let us suppose that the extreme, left extreme end is x is equal to 0. So at that end, a node will be formed. From that, at a distance of lambda by 2, another node will be formed. At lambda, 3 lambda by 2, 2 lambda, etc. are the distances of the positions of nodes from one end. The positions of antinodes are given by x is equal to lambda by 4. So from the end x is equal to 0, at a distance lambda by 4, the first antinode will be formed. The next one will be 3 lambda by 4. And the next one will be 5 lambda by 4. Like this, the antinodes will be formed. The distance between two antinodes or between two successive nodes is lambda by 2. Then there will be no transfer of energy in this wave. Energy is not transferred. The positions where the particles vibrate with maximum amplitude are known as antinodes, and different particles will vibrate with different amplitudes. The speed of the particles at the equilibrium position is not the same. The period is the same for all particles. The frequency will be the same. Particles in adjacent loops will have a phase difference pi. All the particles in the same loop will have the same phase. These are some of the properties of this wave's stationary wave. The speed of the wave on the stretched string, it depends on tension and linear density, and it is given by V is equal to square root of T by M. If a string is vibrated in P loops, then the wavelength of the waveform is lambda is equal to 2L by P, where L is the length of the string. A string of length L, if it is vibrated in P loops, then the wavelength of the wave is 2L by P. The frequency of vibration in this mode, if the string is vibrated in P loops, then the frequency of vibration is given by N is equal to P by 2L into square root of t by m. Like this we can determine the frequency vibration of a stretched string.